Now it is. Sorry. Anyway, silliness. Before we finish off homework 3, are there any questions related to the first 2 homeworks, the first 14 problems we've done here? Any other, class procedure-y sort of questions? Hearing none, let's return to homework 3. I think we were about to start problem 15, and Kevin McPherson has volunteered to be up since he had no power last week, or last Tuesday.
Yep. Let's see. Switch over to my screen. So this one asked for estimating the population size. It's really pretty straightforward. I just listed out all the variables here, have my mutation rate, found H from heterozygote and homozygote sites.
So tell me how you found that was the trickiest part of this question. How did you estimate heterozygosity at these various classes of sites?
Let's see. Hold on one sec. I'm going to pull up the little Word document just to make sure I'm referencing the right thing. Okay, so it says in here that you sequence a single diploid individual with 3 billion single nucleotides, and then you observe that this individual is heterozygote at 3 million of these sites and homozygote at the rest. So in this case, what it looks like I did was
so tell me what the heterozygosity is at a single site where you find one copy of one allele and another copy of another. How do you estimate heterozygosity?
Yeah, that's how did I do it in this? Let's see.
How would you do it in general if I just said go into the population,
yep,
and look at a single locus and estimate heterozygosity at that locus?
I'd probably run some sort of frequency, knowing something about the population.
Yeah. So you'd probably say heterozygosity was, if you knew its allele frequency was P, what would you say its heterozygosity was?
1 minus P.
Is it?
No. Sorry, 2P, 1 minus P.
Yeah, 2PQ. Absolutely. So if I gave you a lot of individuals and asked you what heterozygosity was, you'd figure out what the allele frequency was, and you go, it's 2PQ.
Yep.
I've given you 2 alleles.
Mm-hmm.
What's your estimate of the allele frequency if one of them is A1 and the other is A2?
Yeah, I think I'm probably made the assumption based on that 2PQ that's just how the bases also played out in that, or the sites also played out in that case.
Yeah, but each of those sites, you would estimate the frequency was a half.
Yeah.
So you'd estimate 2PQ was a half.
Yeah, that's true. Yeah.
So you'd estimate heterozygosity at those 3 million sites was a half. Whereas it looks like you plugged in 1, as if every single site there were vastly, everybody had a different allele. In fact, there's probably a 2 here that is 2PQ for every single site. Does that make sense?
It does make sense, yeah.
Is everybody else with us? That when you go to estimate heterozygosity is defined as the expected number of heterozygotes, or 2PQ. So for 3 million sites, I have an estimate of P of a half. I only have 2 observations. One of them is A1, the other is A0. So I estimate P to be a half at 3 million sites. At a whole lot of other sites, 3 billion, I estimate P to be 0. So this estimate looks like a half times 3 million plus 0 times a big number divided by 3 billion, and you get exactly a half of your current estimate there. And from that moment onward, everything else in your work is perfect.
Okay.
Just completely plugging along, but and using H and all this is absolutely perfect. But because I mean it's a sample size 2, it's not a very good estimate of P. But my estimate of P is a half. So I've got 2PQ, which is a half, times this thing. Is everyone else with us? So I'll show you my screen just to sort of roll that out just a little more. Where is it? There we go. Share my screen. There we go. So what I say? So 3 million bases, this individual is a heterozygote. My best estimate for the allele frequency at these 3 million bases is a half. So heterozygosity at these 3 million bases is 2 times a half times a half is a half. At all the other bases, my best estimate of allele frequency is 1. So I estimate a heterozygosity of 0. So my naive estimate of heterozygosity is 3 million times a half plus a big number times a billion, 2.7 times a billion times 0 divided by 3.9 divided by 3 billion. And I ended up exactly 1/2 of what Kevin did. Later, we will learn that this is not a very great estimator of heterozygosity, that it's actually a biased estimate. And we'll actually learn that Kevin's guess turned out to be a better estimator than mine because it actually used an unbiasing factor and it got it much closer to the correct answer. But we won't see that until later on in the chapter. And from that moment on, just plug in, I got 4NU equals H over 1 minus H, and therefore I got N being exactly twice the value Kevin got because I've used a half of this heterozygosity. Does that make sense?
Oh, sorry.
Yep, go ahead. Or was that
Can you explain why for when you were estimating, you put 3 to the 9th on the bottom?
Because that's a typo. It should say 3 times 10 to the 9th. Pure typo. That should say 3 billion. I even read it as 3 billion. But it should say 3 billion. Much like the top says 2.7 times 10 to the 9th.
Can you repeat why you were able to estimate the first 1/2, so the frequency at the 3 million?
So I've got a single individual. My individual has 2 alleles. One of those alleles is, we'll say, is A1. The other allele is, say, A2. Half of the alleles are A1. Half of the alleles are A2. In my sample of size 2, which is a pretty lousy sample, half the alleles are A1. So I estimate its frequency to be a half. Pretty ugly estimator. Not a very good one, but it is what it is.
Is that assuming that none of these bases are within the same like locus, I guess? Each one is a separate segregating allele?
Yeah. I've estimated as a per site heterozygosity over the entire genome. Yeah. As if every single site was an independent locus. And this is the average over the genome. So this is genome-wide heterozygosity per site. If I hadn't divided by 3 billion at the end, I would have gotten an estimate of genome-wide heterozygosity as that number times 3 billion. Or per site, that number divided by 3 billion. Questions?
So I definitely didn't get the right answer for this, but I approached it with a slightly different manner of thinking, and I kind of just want to think about where I might have gone wrong.
Yep.
But basically, I was thinking about it more in terms of, well, you sort of have your frequency already where you have your total number of sites, right? Or you have your total number of nucleotides, but you could get a frequency by dividing by the number of heterozygous sites, like I think what Kevin did. And then I was thinking about it in terms of that equation where you relate alleles to frequency. So PI over AI over 2N, or the frequency is A. But I think once I started to do that, I started squaring things, and I took the square root, and I ended up getting a very large number that I didn't expect to get.
Do you want to show it precisely, or
Sure, yeah. I mean, it's a little
it's a little messy, so to speak?
but I'll go ahead and I'll share just for that thinking process. Okay, 1 second. So yeah, it's not exactly right, but
Yeah, so you started off thinking that
it's a pretty large number, and I already was thinking like that's very large for a population. I don't think that's right, but
that is very large for a population. So what did you so we started off by saying you start off with the same argument Kevin did, basically, that if 1 in 1,000 sites are heterozygotes, that must mean heterozygosity is 1 in 1,000. Okay, it's an estimate. But from there, what did you do? You said P1 is equal to A1 over 2N.
And so then what I did was I put in I think what it was, now that I'm showing it, is I had the frequency of the allele. So I think maybe what I assumed was that for heterozygous sites.
Frequency.
Yeah, so what I wanted to do was put in a number for this allele using one of the values that I had either calculated or subtracted out. And then I wanted to use my frequency. And then could basically like take out the N here to find it. But now I'm kind of seeing where I might have gone wrong on that, because I think
this just doesn't fully make sense, what we've done below. The best way to think about this problem really is as with regard to Jim's last question. It's like you have 3 billion different loci. At each locus, you have an estimate of heterozygosity, and you're taking the average over your 3 billion loci, as if they were different from one another. And then from that genome-wide average, you're then calculating theta. And the formula you were using makes perfect sense at a single locus, but not so much sense when we're talking about different loci.
Okay.
And that this is definitely the best way to think about this is that these are 3 billion different loci, and we're combining them to gain a gross estimate, as if each of the loci were the same in some fashion, to gain a genome-wide average.
I also did this incorrectly. And I was wondering why it's overly simplistic to just think of it as a ratio, because I thought of heterozygosity as the probability that 2 alleles picked at random are going to be different. And so I did just say, that 3 billion times they are different, and that's out of 3 million total. And so I also did what Kevin did and just put 3 million over 3 billion. Because conceptually that made sense to me, but I'm kind of still missing, I think, where the averaging comes in.
So that turns out to be a better estimator than the one I'm giving you. The estimator I'm giving you is, it takes heterozygosity at each locus, at each of the 3 billion sites, and averages them. So if it turns out the estimator at each of the individual loci was itself a biased estimator, when I combine 3 billion biased estimators, I end up with a biased estimate again. And your little piece of logic is very, very close to the logic that creates an unbiased estimator of variance. So you might imagine from other things you've done. See, right, each of those heterozygosities is just a variance, really. And you guys probably know that when you estimate variance from a sample, the estimate of variance is biased, and that the biasing factor turns out to be n over n minus 1. So at each of the 3 billion loci, I've estimated the variance, but I've estimated that variance with a n over n minus 1 bias to it. So when I combine all of them, I've repeated my n over n minus 1 bias and ended up with a estimate of heterozygosity that is biased by a factor of n over n minus 1. Here n is 2, so it's off by a factor of 2. So I asked you to average the variances, and you're going to end up with a biased estimate. And you've come up with an argument that happens to result in an unbiased estimator of that variance.
Where does this bias get introduced in the averaging calculation? This n times n minus 1 bias.
So, right, at every locus, I've estimated its variance in the allele frequency. That variance is 2pq. So that is an estimate of the variance of the locus. You know, from in many contexts, when you sample something and estimate the variance from the sample, your variance estimator is biased by a factor of n over n minus 1. You've probably encountered that before when trying to estimate variances. Like, you guys have probably learned that you're supposed to, when you take a sample variance, you're supposed to multiply it in the end by n times n minus 1, n over n minus 1. It is you're unbiasing that variance estimator. You're making the expectation of your estimator equal the true variance. And the expectation of 2pq, when I estimate p and q for my sample size, is not the true estimate of variance. It's n, and we could prove it if we wanted to. Does that make some sense?
Yes, I'll have to find my previous math teachers and ask why they let me down.
Well, I'll show it to you offline if you like. Anyway, so your intuition that everybody's intuition that a better estimator of heterozygosity might be the total number of heterozygotes divided by the total sites when estimated in a sample of size 2 is correct. A better estimator of heterozygosity, though, in a larger sample size is going to be 2pq summed over all sites times n over n minus 1, where n is your sample size. And if you want to do it per site, divided by the number of sites. And we will see that later in the chapter. But 2pq summed over all sites is a much better estimator of heterozygosity than just counting heterozygous sites, unless you have a sample size as crummy as 2.
Okay, thanks.
Other questions? All right, let's move on to problem 16 with Linnea. Sure.
All right, I'm here.
There.
Sorry, 1 second.
Yep, no, take time. Oh, this mess. Yes.
Okay. Yeah, all righty. So 16. Okay. So just
There you
going
go.
over the
This
question for a sec. Yeah, okay. So basically we had to find the exact value of delta H, I think.
Yep.
Or no, you want the, because we want the equilibrium, so that means we have to set delta H equal to 0. And in the book, they give a estimate as to what it is, but if you take, this equation here, 2.8, and do a bunch of algebra, you can manipulate it to get delta H.
Yep.
So the way that happens, you just sub in 1 minus H prime here, and then 1 minus H, multiply a bunch of stuff out. But the key is that on this side, we're going to have that this delta H, this H prime, you can bring it over here, and then basically you can see that, yeah, it's basically just algebra, but you can see that you'll be able to get an H prime minus H here, which is the thing that you want to set equal to 0.
Mm-hmm.
And then, yeah, sorry, I don't know if that's confusing because I kind of just went over that really fast, but you basically just multiply it all out, and then you sort of look for this factor and you set equal to 0, and then you solve for H, and this is the actual H value, as opposed to the approximation they gave you earlier, which is here. And then from there, sorry, okay, so we go ahead and just plug in a bunch of values and see what happens. So I guess their argument was that this approximation is valid when the mutation rate is very small and the population size is very large. So I guess we're trying to see which one of those things matters more, I guess. So what I did, I just went ahead and plugged them in. So when U is kind of large, N is small, they still have the same order of magnitude. U is large, N is pretty large, they're very close. U is very small, N is, I guess, kind of small. Their difference in magnitude is like 3 orders of magnitude, and about the same when U is very small, N is very large. So I just said, well, then it looks like if U is small, then our approximation is not really that good.
Yeah, if this were ever 3 orders of magnitude apart, I think we've gotten the algebra wrong somewhere.
Oh, okay. Yeah, I might have gotten something wrong here.
This wouldn't be stunning if somewhere in here the algebra was went a little funky. This is utterly correct. Everything you've done is utterly correct. Your setup is utterly correct. Your approach is utterly correct. And plugging in the values at the end is completely correct. I think there's probably some little piece of algebra gone funky in the middle. Okay. So when I did it, I got H was equal to 1 over 2n times 1 minus mu squared, or rather I got G is equal to 1 over 2n times 1 minus mu squared. And on the bottom, I got 1 minus mu squared minus 1 over 2n times 1 minus mu squared. And so I got H of 1 minus that. There's, I'm sure, a million other formats you could write this in. Literally an arbitrarily large number of them. And, but your approach is exactly right. That at equilibrium, G is unchanging. This is sort of how I just solved it. I just said at equilibrium, delta G is unchanging. So you have the same G's on both sides. Solve for that G, and you get blump-de-dee-blump. And then 1 minus H is that. I mean, 1 minus G is that. So anyway, as a result, when you get it exactly correct, the approximation looks even better than it did to Linnea. So when n is 10 and u is 0.1, the approximate gives me 0.8, but the exact gives me 82%. So it's only like about 3% off. When n is 1,000, I get like less than 1,000th off. When mu is small, I get almost the same answer to like 4 significant digits. So when n is very tiny, like 10, there's a measurable difference maybe. But when n gets large, there's not even a measurable difference for almost any value of mu that makes sense. So while this is not exact, this approximation is probably pretty good, unless unless your population size is tiny. And there's probably no such thing as that in nature. So anything in nature is probably like, this has to be some sort of weird experimental system in a bottle if you have n of 10. Otherwise, these sort of equilibrium numbers are probably good enough for you. Does that make sense?
Yeah, that definitely makes more sense.
And it was just algebra that killed you. I mean, you can sort of see.
Okay.
And I didn't really do any. That's why I got it right, because I just expanded it. Left it alone.
Why did they create an estimate in the first place? I didn't understand that.
So look at my formula for G. G is equal to 1 over 1 plus theta. That's the estimate. I can remember 1 over 1 plus theta
Yeah.
for my forever and ever and ever. Try to remember that. Go ahead. Memorize it. You will never get it right again in your life. So 1 over 1 plus theta is easy, 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 easy to remember. Theta over 1 plus theta is super easy to remember. This piece of crap is unusable by anything other than a computer program. And unless n is terribly tiny, the approximation gives the correct answer to 4 significant digits anyway. So this is population genetics. It's not rocket science. If we're off in the 4th significant digit, nothing blows up. So it'll be okay. Does that make sense? So Taylor, you're up with whatever the next one is, 16 maybe, 17. Oh, 17 is fine.
Okay. So for problem number 17, we are considering a single locus with 2 alleles and no mutation. We're assuming that A1 allele exists only in a single copy, so the initial frequency is just 1 over 2n. The current heterozygosity, the way I calculated, oh, I forgot to share my screen. Okay, so since there's only 1 copy of the A1 allele in the current population, I assume that means there's only 1 heterozygous individual, and thus the probability of being a heterozygote is just 1 over n. However, we know from reading that without mutation, eventually 1 allele, either A1 or A2, will ultimately be the ancestor allele of all the alleles in the population, and so all variation will be lost. Thus, we can assume for a very large T, ZT, which is just what I called the number of copies of the A1 allele, and generation T will ultimately only take values 0 or 2n. And by problem 4, we know that the expectation of the number of A1 alleles in generation T is just 2n times the initial frequency. Here, that frequency is 1 over 2n, so we just have an expectation of 1. But by the definition of expectation, we can write that 1 is equal to 2n times the probability that ZT equals 2n, plus 0 times the probability that ZT equals 0, since those are the only 2 values it would ultimately take. And the 0 term drops out, and we're left with 1 equals 2n times the probability that ZT equals 2n. And the probability that ZT equals 2n is the probability that the A1 allele will ultimately fix in the generation, and that's just equal to the initial frequency, 1 over 2n. And similarly, we can calculate the probability that the A1 allele will ultimately be lost as just 1 minus the probability that it will be fixed, since it can only take values 0 or 2n, and that's 1 minus 1 over 2n.
That's it. So that's the ballgame. So what did we learn? The allele frequency on average is its starting frequency. It's whatever it is right now, the expectation of the allele frequency. But the expectation of the variance is 0, meaning the allele frequency is going to go to 0 or 1 sooner or later. So the mean frequency is 1 over 2n. The variance is 0, meaning it must be either 0 or 1. So the mean must be the probability that it is at 1 times 1 plus the probability that it is at 0 times 0. And that has to equal its current frequency, 1 over 2n. That's how we learn the probability of a newly arising mutation at frequency 1 over 2n. The probability that it will ultimately fix in the population is 1 over 2n. The probability of an allele currently at frequency 0.5 will ultimately fix in the population is a half. Its frequency is 0.1, probability ultimately fixes 0.1. That's a result you can keep in your head. An allele at frequency x has probability x of eventually reaching frequency 1 before it's lost. And probability 1 minus x of being lost before it reaches frequency 1. That is a deep, deep, and powerful result. And it is fundamentally the reason, say, the neutral rate of evolution is independent of population size. Alleles that arise in a population have exactly the population, 1 over the population size of fixing. We will see how that cancels, and we get a rate of evolution that is independent of population size for neutral mutations. That'll be a very, very deep result. Does this all make sense?
So if I have that correct, you said that the frequency of allele is also the possibility that it becomes fixed or lost in the population?
Probability it becomes fixed. 1 minus its frequency is the probability it becomes lost.
Okay. And why is that? Is that because of neutral theory, or is that?
Yep. It is because of this argument. Only this argument. This is the entire sort of intuition that for an allele undergoing nothing more than random sampling, that's neutrality. We'll see how selection is different from random sampling according to its frequency. But if you just random sample according to the allele's frequency, the expected frequency doesn't change over time. Mm-hmm. The variance in frequency goes to 0, which means the actual frequency must be 0 or 1. Mm-hmm. So the probability of being 1 times 1 plus the probability of being 0 times 0 has to equal its current frequency. Therefore, 1 times the probability of it being 1 ultimately is its current frequency.
I think that was such a nice bow on neutral theory. I learned neutral theory in a molecular genetics and evolution class by Yokoyama, and I did not get it at all. So
yep,
that makes a lot of sense. So
it is a deep and powerful result. Mm-hmm. There is a reason most of us know the name Moto Kimura. Mm-hmm. And there are a lot of powerful things, a lot of clean, beautiful math arguments you can get when you assume there is nothing going on other than random sampling of alleles proportional to their frequency. And you can get a lot of results, a whole lot of results. This is just the first.
That's very cool.
Other questions? So we will apply this formula maybe a little bit in the next homework to talk about maybe things about rates of evolution. And maybe the homework after that too a little bit. I can't remember. Next week's homework is much of the same, more genetic drift and mutation, and that's it. Sort of classic neutral population. Does anybody have any questions about homework? Well, does anybody have any questions about homework 3 before we move on to homework 4? Okay, does anybody have any questions about homework 4?
For question number 3, I feel like it's building for a lot of the other questions, and I want to make sure I get it right before I get too far. But it's asking to basically come up with some sort of function of how the generations, every 5 generations, the population doubles.
Yeah.
And
Because
I'm
this,
just not quite capable of doing that. Is there a way
yep.
to explain it?
Let me go through. Well, this was a very silly artificial problem, but let's set it up, shall we? So because there's a take-home message I want you to get from this set of problems that has to do with boy, it doesn't want to share my preview right now. Why doesn't it want to share my preview? I can't imagine why it doesn't want to share my preview. Let's try again. Share screen. I think preview. So what we're going to try to get out of this ultimately is that a harmonic mean is a whole lot smaller than anything like a normal mean or geometric mean or anything else you might have heard of. And we're going to see that through this incredibly artificial problem that I've created. So the idea is this population is going through these sort of cyclic changes. Every 5 generations, the population size doubles, and it maintains that size for 5 generations, and then it doubles again, it doubles again, it doubles again, until it gets to size a billion, and then it stays there for 5 generations, and then it shrinks by half, and then it shrinks by half, and then it shrinks by half, and so forth, until it gets to size 1 or size 1. Is that what I said? Until it gets to size 1, and then it stays there for 5, then it starts doubling and it repeats over and over. So its current size is size 2. The population will be there for 5 years, and then it'll be size 2 squared. In 10 years, it'll be size 2 to the 3rd. And just so you know, a billion is a number between 2 to the 29th and 2 to the 30th. So once it gets to 2 to the 30th, it'll stay there for 5 generations. And then it'll start going back down. So this whole sort of cycle takes like 145 years or something to get there, and it spends 5 years at each. It spends 5 years at each size going up, spends 5 years at the top, then spends 5 years at each size going down, spends 5 years at the bottom. So each size in between, it spends 10 years, but at its top size and its bottom size, it spends only 5 years. So if, say, you were trying to do in a normal mean, you would say that at its top and bottom size, it spends 1/60th of its time, and at every size in between, it spends about 1/30th of its time. If we've counted this up correctly, the sort of 30 steps. So 1/60th of the time it's at size 1, 1/60th of the time it's at 2 to the 30th, 1/30th of the time it's at all these steps in between.
How do you get the 60 and 30? I'm not.
I added and then did a little subtraction. So 5 plus 5 plus 5 plus, so that's 5 30s going up. but I don't duplicate that top one. So I come down in some other number of fives. So I've doubled each of I've got 5 years in every step at size 2, 4, 8, 2 to the 29. So I've got 2 of those, but only one at size top and one at size bottom. And so it turned out there are 29 steps. 1/30th of the time it's at each of those, and 1/30th of the time it's at the top and bottom size. Put together, they're another 10. Maybe that's the easiest way to say it. There are 29 steps where it spends 10 years, and there are 2 steps where it spends 5 years. So in total, it's 1/30th for each of those, and 1/60th for the top and bottom.
Because together they should basically become 1/30.
Exactly. Yep.
Yeah.
Together, they are the top and bottom step are the same length of time as all the other steps. The top and bottom step put together are the same length of time as all the intermediate steps. But honestly, if you get some other probabilities in here, we don't really care very much. What we're going to really be interested in is showing that harmonic means your intuition for what a harmonic mean, that you might not have an intuition for what a harmonic mean is before you do this math. And afterwards, your intuition for what a harmonic mean is really, really small compared to, say, arithmetics. It is much closer to a number resembling the smallest something gets than it is to its mean or to its just about anything else. It tends to look like the smallest value a random variable can obtain rather than much of anything else. And that will be important because it will be Ney's explanation for why heterozygosity is the same in all organisms. But we're going to do math on these stupid harmonic meany things so we can understand why Ney believes, well, how Ney explains the fact that all organisms have roughly the same heterozygosity. Because that is a fact. Almost anything you look at, and you look at the amount of variation in it, it's about the same as humans or flies or mice or anything. It's about the same. To a factor of 10 maybe. Despite the fact that you already know heterozygosity should be theta over 1 plus theta, and theta has population size buried in it. And population size for a fly really ought to be bigger than population size for an elephant. We know there are a lot more flies than elephants. What the hell? And the argument is going to turn out that heterozygosity, the appropriate averaging for heterozygosity, is not the arithmetic mean, but the harmonic. And harmonic means are very close to the smallest value ever obtained. So if all populations at one point or another had the same minimum, they would all have the same heterozygosity. That's going to be a deep molecular evolution argument that we're going to get to by doing stupid little cycling problems and estimating harmonic means. Other questions?
I'm actually, does anyone else have questions before question 10, 11, 12, 13?
Yeah, you're on it. Question 10. So we're going to do some exact, well, more or less exact analysis of a coalescent of size 2. So if you've read the chapter so far, what it's going to teach you is that when one of the more interesting and powerful ways to think about a population undergoing just binomial sampling is via this coalescent view. And the coalescent view is you pick, well, let's start with the sample size 2. If you have 2 alleles right now, you sort of can think about those 2 alleles as having a common ancestor at some point in the past. In fact, we sort of saw the argument, the probability they had a common ancestor last generation was something like 1/2n. The probability they had a common ancestor 2 generations ago is probably 1 minus 1/2n. The probability they didn't have a common ancestor this generation times 1/2n. The probability they had a common ancestor the year before that, the generation before that. The probability they had a common ancestor 3 generations ago probably looks like 1 minus 1/2n to the squared times 1/2n. The probability they had a common ancestor a long time ago might be 1 minus 1/2n to the t times 1/2n. For a sufficiently large n, we're going to approximate that distribution, which is literally a geometric distribution, with an exponential distribution. So the probability 2 alleles had a common ancestor t generations ago, we are going to approximate as that probability, the probability 2 alleles had a common ancestor t generations ago, with 1/2n e to the minus t over 2n. And the book is probably going to derive that for you. Now, the beauty of coalescent theory is it sort of observes that once you know the tree, once you know the number of generations these 2 alleles are separated from each other, the probability that there are k mutations since the common ancestor is simply Poisson distributed. Mutations are rare events. They happen unusually. So for most rare events, they're probably well approximated with a Poisson. So given that I knew these 2 alleles shared a common ancestor t generations ago, the probability there are exactly k mutations separating them, given that their common ancestor was t generations ago, is just some Poisson distribution. It is a Poisson with mean, the mutation rate times the time to the common ancestor times 2, because I have t generations back to the common ancestor and t generations down again. So I expect the number of differences to be Poisson distributed with mean equal to the mutation rate times the time since they had a common ancestor times 2. So this is a Poisson with mean 2 mu t, which means that's the form e to the minus mean to the k over k factorial. And the problem asks you, since I don't know how long ago they had a common ancestor, it might have been just a little bit ago, or it could have been infinitely long in the past. I have to integrate over all possible values of the time since the common ancestor. So I have the probability the time was t, I have the number of mutations given the time was t, integrated over all possible values of t. That will give you the correct answer. That will give you the correct answer every time. There's a good chance you're going to be unable to solve that integral unless you happen to know what a gamma function is. And a gamma function, one definition of gamma of z, is the integral from 0 to infinity of x to the minus z, e to the minus x dx. And it turns out I'm going to be able to make this mess here look like a gamma function, and I'm going to replace that ugly integral with a gamma function And it also turns out that for a gamma function is actually a generalization of a factorial to real numbers. So if you put an integer in a gamma function, you get nothing other than that integer minus 1 factorial. So this ugly, 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 ugly integral is going to become a gamma function of an integer that you're then going to replace with a factorial. And you're going to do math and math and math and find the answer was 1 over 1 plus theta times theta over 1 plus theta raised to the k. Equilibrium homozygosity times heterozygosity raised to the k. That's what you're going to get when you do the ugly math in between. It's an astonishingly simple result. 1 over 1 plus theta times theta over 1 plus theta raised to the k shall be your answer if you did the transformation of variables correct, you found the gamma function correctly, and you were able to do a little bit of algebra correctly. This is the hardest problem you shall see this year in terms of it is a transformation of variables piece of calculus and requires that you recognize the existence of a non-elementary function. But the result is magnificent. You can write down the probability of exactly k differences in terms of equilibrium homozygosity times heterozygosity raised. Astonishing. And then the rest of this is going to ask you about stuff like what is the mean? This is a geometric distribution. It is the definition of a geometric distribution. So its mean is lookupable. It is a geometric distribution. So its variance is lookupable. You could probably prove it if you wanted to, but you could also just look it up. So you will find that its mean and its variance are very simple functions of theta. The problem after that is going to ask you to find a maximum likelihood estimator of theta. So you're going to take your probability, you're going to differentiate with respect to theta, set that equal to 0 and solve. You're going to get something astonishingly simple. It's going to turn out if you had first taken the log of both sides, you would have gotten the answer even quicker. But it's not really all that important which way around you do it. You can differentiate with either side. But these problems, number 10, which is a fuck ton of nasty algebra and a little calculus, followed by 11, which is look up a geometric distribution, followed by 12, look up a geometric distribution, followed by 13, derive what the best estimator of geometric distribution is. Or here, really. What you're going to see is that you see theta and you see the observed number of sites over and over again. Over and over and over again. You will see in a sample of size 2, the observed number of sites is an estimator of theta, lots of different ways. And the variance in sites is a simple function of theta. It's all theta. There is nothing to see here other than theta. You get theta over theta, you get 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 theta. Maybe you get theta squared. Maybe you get theta plus theta squared. I'm having you do all of this for no reason other than to see that when you set this up as a random time to a common ancestor and a Poisson distributed number of events, the thing that controls that process entirely is theta. There's nothing else to it. And That's why we're going to walk out of our neutral theory section, our random sampling from a population undergoing drift and mutation, knowing that everything there is to know about this little stupid thing is summarizable by theta. In larger sample sizes, you may get more complicated formulas for theta. But by God, there's nothing to see here beyond theta. Does that make sense to everybody? So, if you are good at these sorts of things, go ahead, get that geometric distribution. Find the gamma function, do a transformation of variables successfully. Remember your Jacobian, because if you don't have that, you will definitely screw that up. Do the transformation of variables successfully, and find your gamma function. Realize you've got a gamma of an integer, and it'll all be smooth sailing for you. And if you like this sort of thing, have fun with it. If you don't, write down the answer that the probability that there are k differences is g times h to the k, where g is 1 over 1 plus theta and h is theta over 1 plus theta. And move along to the rest of the problems. Does that make sense to everybody? Could be fun if you like this, and if it isn't, know the result you're headed to. Other questions? Nothing you do in this class is going to be more mathy than those 4 problems. That's it. This is the hardest you're going to get pushed. So to the extent that that is easy for you, you're in great shape. And to the extent that this is hard for you, know this is the hardest it is going to get in terms of mathiness. Other questions? Okay. So these last 2 homeworks are as long and as hard as anything in the class. Once you get through them, 5, 6, 7, maybe 8, 5, 6, 7, 8 are going to be much more application-y, much more special casey things. You know, the selection stuff tends to be a lot easier. Well, once we have the neutral formulations, selection stuff tends to be a lot easier and a lot more plug and play kind of stuff. And it should be smooth sailing for you guys until we hit quantitative genetics. But when we hit quantitative genetics, it's going to be applications of the definition of mean, variance, and covariance until you are dead sick of it. Over and over and over and over again, we'll be applying these definitions to derive ultimately the correlation between relatives. There are some incredibly slick results that are actually nothing more than simple application of definitions of means, variances, and covariances. But you'll derive them all in homework 9. But these are the 2 humps in the class. This one and homework 9. And you guys are doing great so far. Other questions? So when you really do the homework yourself and you run into some place that is making you want to pull your hair out, drop me an email, and I'll give you a hint for how to get by it with more of your hair, even though some of us don't have any. Otherwise, do your best and have fun. See you next week if there's nothing more.